Section 1.3, Vectors. Properties can be described usually with magnitudes. So we could think about speed. So speed, I could have a speed of 1. I could have a speed of 100. I could have a speed of 1,000. Speed is an absolute value of velocity, so speed can only be positive. But anyways, we call speed a scalar quantity because it has magnitude. The speed of something, at least one-dimensionally, is something that could be small or could be large. We only define it by its magnitude. So this magnitude is described by something called a scalar. However, we have other quantities that need to be described by vectors. So vectors are things. So vectors have, and this is a definition, magnitude and direction. So we can use vectors to describe multi-dimensional movement. So I could use a geometric vector between 2 points. So how about we have a scenario where my friend is at point O and I am at point A. Well, we could use a vector to describe where I am in relation to my friend at point O. So this could be a vector. We could call this vector A. And A will have a length, so the distance that we are, but it will also have a direction. So let's say I have like a compass rose. I could have a compass rose to tell my friend which way he needs to go. And he needs to go about like that way, right? So I think that's east there, and this is north. So he needs to go northeast to some angle, theta. So I can tell him where I want him to go using a vector. So if I have a vector A, then the magnitude of vector A we denote, so given vector A, we can have the magnitude. And for the magnitude, we don't put the little arrow on top. We just write the letter. So the magnitude is just the little A guy there. So to describe these vectors, we are going to need some operations. So we are going to look at addition of vectors, and we're going to look at some multiplication of vectors. So we could define given vector B, we could have vector B, and this could be equal to some constant lambda times vector A. And this vector, or this scalar quantity lambda, is going to be in the real numbers. So thus, we can say that B equals lambda A as well. And B is also going to be parallel to A, because all we need do to change A to B is multiply it by some values. So here we have vector B, say this is vector B here, then vector A probably be something like this. It would be parallel to it, but it might be a little bit shorter. So to construct B from A, we multiply A by some constant, and that will stretch A or shrink A, or make A negative. If I want negative A, then I would multiply it by a negative number, and that would give us a negative vector, a vector that's the opposite direction on the straight line. So I could make B out of lambda many A's, and because they're parallel. So if this lambda value is going to be greater than 0, then both of the vectors are going to be in the same direction. But If it's less than 0, then they're going to be in the opposite direction because we're multiplying the vector by a negative number. Okay, now we also have rules for vector addition, so we can add vectors. So to add these vectors, say I have vector B and vector A. Well, to make vector C, all that we do is we add these vectors from, we line them up tip to tail, so we'll move B to the tip of A, and then from this we can get vector C, and that will be vector C. Let's move this B out of the way though. So this is going to be vector C, which is vector A plus B. So that's how we add these vectors. And we are going to need to do this mathematically though. So a couple of properties for adding vectors. Here's another definition. So if I want to add vectors A and B, so if I add A and B, it's not going to matter which order I put them in. So that's going to be the same as adding vector B plus vector A. Likewise, if I do vector A plus B, well, we can take this by component. So each vector has something called a component. We'll get into this later, but essentially, vector A here would have an x component for the horizontal and the y component, and it's some combination of x components and y components. So the way that we add these vectors is if we can separate these vectors into x and y components, then we add the components together. So this would be the same as A sub x plus B sub x times the unit vector for x, E hat sub x, plus A sub x plus, or A sub y plus B sub y times the basis vector for y, E sub y. And we can make this a little bit more compact by using something called the Einstein summation convention. And this basically says that we're just going to index this, so we only need to write it once. So A sub I plus B sub I times the unit vector E sub I. So this means I can take values of x, y. I will take values of whatever you need it to solve your problem. So if A is a vector and B is a vector, then we can also define something called linearity if we have alpha and beta as constants. So we can build something called a vector space that we're going to be working with by exploiting this property of linearity. So another definition. If alpha and beta are constants in the real numbers, then we can define a vector space such that C equals alpha times vector A plus beta times vector B. So essentially what this is saying is using constants, vectors, and their sum properties, I can define a new vector from those two vectors and two constants. So we've created a vector space. Okay, and there's another set of vectors that I kind of talked about with that E sub I and E sub x and E sub y, called the basis vectors. So basis vectors are something that you learn about a lot in linear algebra work, but we're going to be using it in physics here as well. But basically, if we have two vectors that are not parallel, so two basis vectors that are not parallel, so we'll call this one E sub u, we'll call this one E sub v, and these can't be parallel. Then we have another vector A. We have another vector A. Then what we can do is we can take these vectors and we can write vector A as a sum of components. So vector A can be written as some amount of the v direction, so A sub v times E sub v plus A sub u times E sub u. So we can decompose A into components of E sub v and E sub u. And we draw like a nice little parallelogram, and these will all be in the same direction as vectors that we have for the basis. Okay, so we can write A as a sum of vectors that are, of scalars that are multiplied to basis vectors. So each of the elements in this sum here is called a component. So we have a v component and a u component in that expression. So we call usually these vectors e sub v and e sub u, these are usually e sub x and e sub y. And on an xy coordinate plane, coordinate plane, we have a vector A here. We have a unit vector here, a basis vector e sub x, and a basis vector here, e sub y. We can write A as some amount of e sub x plus some amount of e sub y. And then we can write A equals a sub x, e sub x, plus a sub y, e sub y. That's how we work with components a lot. Now, if we want to find the magnitude of our vector from the components, then we can make use of the Pythagorean theorem, because this, of course, makes a right triangle. So here we have another definition. If I want to find the magnitude of A given a sub x and a sub y, then I can define the magnitude A as being the square root of a sub x squared plus a sub y squared. It's the same as the distance formula. And let's say I had a 3-dimensional vector, a 4-dimensional vector, a 5-dimensional vector. I could keep using the Pythagorean theorem just with more parts of the summation. Okay, so again, we can take vectors as scalars, and I'm just going to write a little bit more just for notation's sake. But if I have vector B, vector B being lambda times vector A, well then vector B is going to be B sub x times E hat sub x plus B sub y, E hat sub y. And we can write this as lambda times A, E hat sub x plus, or A sub x, E hat sub x plus A sub y, E hat sub y. Okay, and this is equal to lambda A sub x, E hat sub x plus lambda A sub y, E hat sub y. Okay, and we can write this again in a new notation. This is column vector notation. So this is technically a matrix, but we treat it just like a vector. So I have two components, B sub x and B sub y. We draw parentheses around it, and that is equal to lambda times A sub x, A sub y. These are our components for our vector. Now, something important that we can look at is we can define a vector in terms of its components, but we can also define it in terms of direction and magnitude. So, of course, I have A sub x here, and I have A sub y here, but I also have two other quantities that I know. I could know the magnitude, and I could also know the angle from the x-axis. So from this, we can define A sub x as being equal to the magnitude times the cosine of theta, and A sub y is equal to the magnitude times the sine of theta. This is going to be very important because usually it's easier to know the direction and the magnitude as opposed to the components. So let's do an example of vector addition real quick. So for vector addition, I have, let's define A as being equal to 2, 0, or 2, 0, and B will be defined as being -1, -1. So let's say I want to find a vector C such that C equals A plus B. Well, this is going to be 2, 0 plus -1, -1, which is equal to 1, -1. We can take these components, so 2 minus 1 is 1, 0 minus 1 is -1. Wonderful. So that's how we do the addition. Okay, finally, I would like to discuss vector functions. Now, vector functions are how we model positions of different objects. So let's say that I have a particle moving. It's moving around, and I can define a coordinate system. And here's my particle right here. And it's going along some trajectory. And I can define it from the origin as a vector at each point in time. We define this vector r of t. Now, r of t can be defined by its components. R of t equals x of t and y of t by its components. Now, let's see what happens when I want to take the derivative of a vector function, because this is important, because if I know r of t, well, then I'm going to need to determine what v of t is and a of t. This is different from the one-dimensional kinematics case where we just could take the derivative, because now we have multiple components that we're dealing with. So let's say I want to differentiate, so I want to find dr dt. Well, this is going to be equal to the derivative with respect to time of x of t, e hat sub x, plus y of t, e hat sub y. Okay, and using the linearity of the derivative, we can rewrite this so that this becomes the time derivative of x of t, e hat sub x, plus the derivative with respect to t of y of t, e hat sub y. And this becomes dx dt e hat sub x plus dy dt e hat sub y. Now, what this essentially means is that if I have a vector function that can be written in its components, then I can take the components separately when doing limits, when doing derivatives, and when doing integrals. So vector functions can be separated by components for calculus operations. And that's really what we need for our two-dimensional kinematics, which we'll talk about in the next video. Thanks for watching.